an ever-changing world, it's not just our mindset, political views, or landscapes which are changing. Even down to the most minute detail, our world is reshaping and remodeling itself every second of every day. Now, this can be seen as very beneficial, such as the erosion of sea rock to create beautiful arches to inspire our artists. However, there is one group of organisms which poses a great threat to human life due to their ability to evolve rapidly and adapt to change. Bacterial drug resistance is increasingly worrying scientists. We, as a species, have ingested so many antibiotics in such a short amount of time that it is predicted that by 2050, antimicrobial-resistant infections will be a greater killer than cancer. YouGov suggests that this will cost the world £66 trillion. So, how do antibiotics actually work? Well, here's a generalized diagram of a bacterium cell. These are about 1 to 5 microns long, so that is about 10 to 1,000 times smaller than a full stop. So these are very, very small unicellular organisms. So they need to be protected from outsiders. And to be protected, they have cell walls and a capsule. Now, what antibiotics do is they penetrate this capsule and disintegrate the cell wall, causing the contents of the bacteria to splurge out and causing the bacteria to die. And this is called lysis. However, antibiotics have a very fast reproduction and thus evolution rate. In the time for one bacteria to become resistant, nearly 1 million will become immune to the disease. And because they can evolve so quickly, they have 3 ways which they can exchange genetic information to help them become immune. The first way is DNA transformation. So here the host cell, which contains the resistant gene, releases its DNA into the outside, and a recipient cell in the right state will uptake this DNA and combine it with its own genetic information. This produces a genetic alteration. Now, this seems like quite a simple process. However, the recipient cell must be in the exact state and the exact place in the cell cycle for this to happen. So this doesn't happen very often, and it's not a very efficient way. So a better way, what would a better way be? Well, there is the indirect transfer of genetic information called transduction, using something called a bacteriophage, which is a specialized virus. These phages inject the host cell, which contains the resistant gene, with viral DNA. This then breaks up the bacterial DNA, combines with it, and forms lots and lots of bacteriophages inside it. These bacteriophages also contain some of the viral DNA. When there are so many in there that the pressure is too much, they burst out of the bacteria cell, and one of these viruses will contain the resistant gene. So later on, this phage will go along to another bacteria cell and inject it with the resistance gene. And this gene is then combined with the other DNA of the bacterium cell, and now this one is resistant. This is, again, quite a good way. However, it involves the direct killing of one of the bacterium cells. So we need a way where both the bacterial cells will be alive, but also the recipient cell doesn't have to be in a specialized state. So probably the most important and significant way that bacterium transfer genetic information is through plasmid exchange, called conjugation. Here, the cell will have a hair-like appendage on it that goes towards the recipient cell. And this plasmid, which is a loop of DNA, which usually contains resistance genes, will unwind and unzip itself. Then 2 strands will be formed. One of the strands will travel down the pelus towards the recipient cell. Then, using complementary base pairing, the plasmids will rejoin, and there'll be 1 in each of the bacterium cells. So now, as you can see, both are resistant. So this is by means the most effective way of genetic transfer. It's not difficult for bacteria to exchange information. And if we don't start reducing our intake of antibiotics and finding a new solution, which currently in 2013 stood at 21.5 out of 1,000 people and has risen 6.5% in only the last 4 years, the repercussions will most likely be catastrophic. So how are we responding to this information and these statistics? Well, doctors can prescribe different types of antibiotics depending on the bacterial infection that you have. There are usually two classes of bacteria because bacteria have different types of cell walls. There is gram-positive and gram-negative, and they need to be attacked in different ways. So antibiotics that attack gram-positive bacterial cell walls need to attack a very thick layer of a substance called peptidoglycan, whereas gram-negative only needs a thin layer of peptidoglycan, but you also have to penetrate this lipopolysaccharide layer. If you attack either the gram-positive or the gram-negative with antibiotics, this is called broad-spectrum antibiotics. Doctors can also prescribe medium-spectrum antibiotics to attack a family of bacteria, or they can prescribe narrow-spectrum antibiotics, which attacks one single type of bacterium. But there is also other research into how we can tackle bacterial infections, and this is through the bacteriophages I mentioned earlier. Now, there was bacteriophage research in the 1900s in the former Soviet Republic of Georgia, and in the 1920s and 30s, they were used to treat patients. However, back then there was very little understanding of viruses themselves, and so for these bacteriophages, they weren't understood as well as antibiotics were, and antibiotics were much more readily available. So all of this information was forgotten until now. Scientists are now genetically engineering these bacteriophages to produce these enzymes which they use to cause the cell to explode after they've burst into them, and other ones that disintegrate the biomatrix film and the different codings for the bacteriophage so they can ensure that they're killing the right bacteria. PHARS research is extremely important, and as seen by the MRSA scares and the recent resistance gene found to the antibiotic of last resort, the only antibiotic we have found in the last few years that seems to have no resistance to it, there seems to be nothing now that could stop bacteria from causing loads of pandemics or epidemics. Thank you.